Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question that has lingered at the edge of science and imagination for decades, whether parallel worlds might exist, and why some of our most reliable theories keep whispering that reality could be far larger than it appears. Before you settle in and get cozy, you're always welcome to like this video and subscribe. Only if these calm explorations truly bring you comfort. And when you're ready, feel free to leave a comment letting me know where in the world you're listening from and what time it is for you right now. It's a gentle reminder that we gather from many places, each in our own small pocket of time. Now, you might want to dim the lights, perhaps turn on a fan for a soft background hum, and let your shoulders relax. If your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story, one idea at a time. Tonight we begin not with a bold claim, but with a quiet irregularity, a subtle feature in the oldest light we can see, a place where the universe seemed just a little colder than expected. And sometimes it's the quietest details that open the biggest questions. When you look up at the night sky, it's easy to feel as though you're seeing the universe as it is right now. But in truth, every star, every galaxy is a message sent long ago. Light takes time to travel, and the farther you look, the deeper into the past you see. There is one kind of light, however, that comes from almost the very beginning of everything we know. A faint glow that fills the entire sky, invisible to our eyes but measurable with careful instruments. Scientists call it the cosmic microwave background. You can think of it as the universe's earliest photograph, taken when space had just cooled enough to become transparent. A soft afterglow from a time when the universe was young, dense, and hot. When researchers mapped this ancient light in detail, they expected to see small variations, tiny ripples that would later grow into galaxies and clusters of stars. And for the most part, that's exactly what they found. The map is remarkably uniform with gentle fluctuations that match our best models of how the universe evolved. But within this sea of near-uniform warmth, there is one region that stands out, a patch of sky that appears noticeably colder than the rest, not dramatically so, but enough to draw attention. This region has come to be known simply as the cold spot. At first glance, the cold spot could be dismissed as chance. In any large data set, rare patterns sometimes appear. A slightly darker cloud, a slightly quieter note in a long piece of music. And many scientists still believe this may be the correct explanation, a statistical fluke in an otherwise well-behaved universe. Yet the cold spot has a way of lingering in the conversation. It is larger than most random fluctuations we would expect, and its shape and scale invite questions that refuse to fully fade. Some researchers have suggested that a vast region of emptier than average space, a kind of cosmic void, could explain it. Light passing through such a region might lose a bit of energy, leaving behind a cooler imprint. This idea is cautious, grounded, and consistent with known physics. Others have wondered something more daring, though always carefully phrased. What if this cold patch is not just an absence of matter, but a scar, not from an asteroid or a galaxy, but from something far beyond our visible universe, a subtle bruise left behind by an encounter between our universe and another. To imagine this, picture the universe not as a single, isolated bubble, but as one bubble among many, floating in a vast, expanding cosmic ocean. In some theories of the early universe, space itself grows so rapidly that it never completely stops everywhere. Instead, it forms pockets where expansion slows, creating individual universes like ours. Each pocket cools, forms stars, and follows its own history. If such bubbles exist, then in the distant past, when everything was close together, it is at least conceivable that two could have brushed against one another. Not colliding in a dramatic explosion, but gently enough to leave a faint imprint, a difference in temperature, a subtle irregularity in the oldest light. It's important to pause here and breathe. This is not a declaration of discovery. No one can point to the cold spot and say with certainty that it is evidence of another universe. Science moves more carefully than that, but the reason the idea persists is because it arises naturally from theories that were developed for entirely different reasons, long before anyone worried about cold patches in the sky. What makes the cold spot so compelling is not that it proves anything on its own, but that it sits at an intersection between observation and theory, between what we can measure and what our equations quietly suggest might exist beyond measurement. And this is where our journey truly begins, not with an answer, but with a shift in perspective. The realization that even the most precise maps of the cosmos may contain hints, soft, ambiguous hints, that reality does not end at the edge of what we can see. As we linger with this thought, it becomes clear that the idea of parallel worlds did not emerge from a single anomaly or a single moment of inspiration. It grew slowly, from different corners of physics, each asking its own questions. The cold spot is simply one place where those questions seem to echo a little louder. And as we gently follow those echoes, we'll begin to explore why some of our deepest theories about space, time, and the smallest building blocks of nature keep leading us back to the same quiet possibility that the universe we inhabit may be only one chapter in a much larger story, written across realities we may never directly touch, but can still wonder about as we drift toward rest. When we hear the word proof, it often carries a certain finality, a sense that a question has been closed, sealed, and settled forever. In everyday life, proof feels solid and reassuring, like a locked door or a signed document. But in science, especially when we're speaking about the largest structures in existence, proof tends to speak more softly. Science rarely declares absolute certainty. Instead, it builds confidence gradually, layer by layer, through patterns that keep reappearing, explanations that refuse to break, and ideas that continue to make sense even as new data arrives. This is especially true in cosmology, where we're not experimenting in a laboratory, but listening carefully to faint messages carried across billions of years of space and time. So when we ask whether parallel worlds exist, we're not asking for a single photograph, a single measurement, or a single moment of discovery. We're asking whether multiple independent lines of reasoning are quietly pointing in the same direction. This distinction matters because the multiverse is often misunderstood as an extravagant idea added on top of physics for dramatic effect. In reality, many versions of the multiverse emerge as side effects. They are not invented to solve a mystery directly. They appear when physicists follow theories that already describe our universe extremely well, and then ask what those theories imply when taken seriously, all the way to their edges. Think of it like following a road through a foggy landscape. At first, you only care that the road beneath your feet is solid, and it is. It carries you safely forward. But as you keep walking, shapes begin to appear in the distance. Not sharply defined, not confirmed, but persistent. You didn't set out to find them. They simply emerged as part of the journey. In science, hints work this way. A single anomaly, like the cold spot, is rarely enough to change our understanding of reality. But when anomalies sit comfortably alongside theoretical expectations, they become more interesting. Not because they shout, but because they whisper the same suggestion from different angles. Another important idea to settle gently into place is the difference between what we cannot observe and what is unscientific. It's tempting to think that if something lies beyond direct measurement, it automatically falls outside the realm of science. But history tells a calmer story. For a long time, scientists believed in the existence of particles that could not yet be detected. They trusted these particles because the equations worked better with them than without them. Decades later, experiments finally caught up. The particles were there all along, quietly shaping reality while remaining unseen. In cosmology, the situation is similar, but on a much grander scale. We are limited not just by technology, but by physics itself. Light travels at a finite speed, space expands, horizons form. There are regions of the universe that no signal, no matter how advanced our instruments become, will ever reach. These regions are not hidden behind walls. They're simply too far away in time and space. The key question, then, is not whether we can ever visit other universes, but whether their existence helps us understand the one we already inhabit. And surprisingly often, the answer seems to be yes. As we reflect on this, it becomes helpful to think of science not as a collection of answers, but as a method for asking better questions. When physicists encounter a theory that works remarkably well in every testable domain, they hesitate to discard it simply because it leads to uncomfortable implications. Instead, they ask whether those implications might be telling us something true, even if it feels counterintuitive. This is where the multiverse quietly enters the conversation. Not as a bold proclamation, but as a recurring outcome. Quantum theory, which governs the smallest pieces of matter, has passed every experimental test thrown at it. Inflationary theory, which explains the large-scale structure of the cosmos, has successfully predicted patterns we later observed. When these frameworks are extended carefully, they begin to suggest that our universe may not be alone. It's also worth noting that science does not demand that every idea be directly testable right now. Many accepted concepts were once out of reach. What matters is whether an idea is consistent with what we already know, whether it explains more than it complicates, and whether it offers predictions or expectations that future observations could one day support or challenge. In this sense, the multiverse occupies an unusual but familiar position. It is speculative, yes, but not arbitrary. It grows naturally from equations that already describe atoms, stars and galaxies with extraordinary accuracy. And perhaps most importantly for our gentle exploration tonight, the multiverse is not introduced as an answer to everything. It does not solve all mysteries or erase uncertainty. Instead, it reframes certain questions. Why does our universe look the way it does? Why do its laws sit in a narrow range that allows complexity to arise? Why do some patterns appear slightly unusual, yet not completely inexplicable? Seen this way, the idea of parallel worlds is less about escaping reality, and more about expanding it. It invites us to consider that the universe might be larger, richer, and more patient than our intuition suggests. That what we experience as a single, unfolding story could be part of a vast collection of stories, each written under slightly different conditions. As we let this thought settle, there is no need to rush toward conclusions. Curiosity does not require urgency. Wonder does not demand certainty. For now, it's enough to recognize that science has learned to listen carefully, even when the answers arrive as soft patterns rather than loud declarations. And with that quiet understanding, we can begin to look more closely at the first of several pathways that lead naturally toward the idea of multiple worlds. A pathway that begins not with speculation, but with the simple, steady expansion of space itself. When we say the word observable, it can sound as though it depends on our tools, Bigger telescopes, sharper detectors, more powerful computers. It feels as if the universe is simply waiting for us to improve our technology so we can finally see everything there is to see. But in cosmology, the idea of what is observable is far quieter and far more final than that. The observable universe is not defined by what we are capable of building. It is defined by what is physically possible. Light does not travel instantly. It moves at a finite speed, steady and unwavering, carrying information across space. Because of this, distance and time are woven together. To look far away is to look into the past. The stars you see tonight are not shining as they are now, but as they were when their light began its long journey toward you. Some of that light has been travelling for billions of years. When astronomers say our universe is about 13.8 billion years old, they're not simply guessing. They are reading the timestamps written into the light itself. The oldest light we can detect began its journey when the universe was still young, long before planets, stars, or galaxies like our own had fully formed. Yet here is where intuition begins to falter gently. Even though the universe is roughly 14 billion years old, the observable universe is much larger than 14 billion light-years across. In fact, it stretches to a diameter of about 93 billion light-years. This is not because light has somehow broken its own speed limit, but because space itself has been expanding while the light was travelling. You can imagine it like this. Picture a tiny spark ignited in a rising loaf of bread. As the bread expands in the oven, the distance between points inside it increases. A crumb that starts close to the spark may end up much farther away by the time the spark's glow reaches it. Not because the glow sped up, but because the space in between quietly stretched. This expansion means that the edge of what we can see is not a physical wall. It is a horizon, a boundary set by time, motion, and the structure of space itself. Beyond this horizon there may be more galaxies, more stars, more worlds, but their light has not had enough time to reach us, and in some cases it never will. This is an important and humbling thought. There are regions of reality that are not hidden because they are secret, but because the universe itself does not allow their messages to arrive. No future telescope, no matter how advanced, will be able to retrieve information from beyond certain distances. The limitation is not technological. It is built into the fabric of space and time. As the universe continues to expand, this horizon slowly changes. New regions drift into view as their light finally reaches us. At the same time, other regions recede so rapidly that their light will never arrive. The observable universe is not a fixed bubble, it is a dynamic boundary shaped by cosmic history. Now this naturally raises a quiet but profound question. If there is a boundary to what we can observe, does that boundary also mark the edge of existence? For a long time, it was tempting to think so. It feels comforting to imagine that reality ends where our vision does. But modern cosmology offers no such reassurance. In fact, when scientists examine the large-scale geometry of space, they find something curious. Measurements suggest that the universe is remarkably close to being geometrically flat. Not curved inward like the surface of a sphere, and not curved outward like a saddle, but almost perfectly level, like an endless sheet stretching in all directions. Within the limits of our measurements, space does not seem to wrap back on itself. If space truly is flat on the larger scales, then one possibility is that it extends far beyond the region we can observe, perhaps infinitely far. And if that is the case, then the observable universe is not the whole story. It is just the portion of the story that has had time to reach us. This idea alone opens a door to a subtle form of parallel worlds. Not universes with different laws of physics, but distant regions governed by the same rules, unfolding their own histories beyond our horizon. They are not separated by walls or dimensions, but by time and expansion. In such a vast cosmos, the concept of uniqueness becomes surprisingly delicate. The laws of physics appear to allow only a limited number of ways for matter and energy to arrange themselves in a given region of space. If space extends far enough, those arrangements may repeat. Not by design, not by intention, but simply because there is enough room for every possible configuration to occur somewhere. This is not something we can confirm by travel or observation. It is a logical consequence of combining finite possibilities with immense, perhaps endless space. And while it may feel unsettling to imagine distant regions mirroring aspects of our own, it also invites a calmer perspective. Our experience remains local. Our relationships, our memories, our choices are anchored here, within this horizon of time and light. The possibility that similar patterns exist elsewhere does not erase the meaning of what happens within our own cosmic neighbourhood. Instead, it gently reframes our sense of scale. The universe may be larger than our stories, but our stories still matter within the slice of reality we inhabit. As we rest with this idea, it becomes clear that the multiverse does not always arrive with dramatic collisions or exotic physics. Sometimes it begins quietly with a simple recognition that the universe we see is not the universe in its entirety, but the universe as far as light has been able to travel so far. And as we continue drifting through these ideas, we'll see how this simple horizon of time connects to deeper questions about infinity, repetition, and the strange ways reality behaves when it grows vast beyond ordinary imagination. As we linger with the idea of a cosmic horizon, another question naturally settles into place, almost without asking to be there. If the edge we see is not the edge of existence, then what shape does the universe take beyond our view? Shape may sound like a simple word, but in cosmology it carries a very gentle power. It does not mean the outline of stars or the arrangement of galaxies. It means the geometry of space itself, stretched across distances so vast that intuition has to soften and slow down to keep up. To picture this, it helps to borrow familiar images. Imagine the surface of the Earth. From where you stand, the ground looks flat. Walk a few kilometers, and it still looks flat. Only when you step far enough back do you notice the curve. That curve tells you something important. The surface is finite. Walk far enough in one direction, and you eventually return to where you started. Now imagine a surface that behaves differently, a perfectly flat sheet extending outward without bending. No matter how far you travel, it never curves back on itself. In such a space there is no natural boundary, no place where the journey must end. Cosmologists ask which of these descriptions best matches the universe we live in, and remarkably, when they measure the largest scales of space they can observe, the answer keeps coming back the same. Space appears to be very close to flat. So close, in fact, that if there is any curvature at all, it lies beyond what we can currently detect. This does not prove that the universe is infinite, but it opens the door to that possibility, and once that door is open, it stays open quietly, inviting us to look through. If space extends far beyond our observable horizon, then what we see is only a small patch of a much larger whole. The stars and galaxies we know would be part of a repeating pattern, spread across an expanse too large to ever fully map. This idea does not require new dimensions, new forces, or exotic physics. It follows naturally from combining three simple facts. Space expands, light travels at a finite speed, and the geometry of space appears nearly flat. Together, these facts suggest a universe that may go on far longer than our view allows, And within such a universe, something subtle but profound begins to happen. The laws of physics, as far as we know, are consistent throughout space. They do not change from galaxy to galaxy, or from one cluster of stars to another. That consistency means there are only so many ways matter can arrange itself within a given region. Stars form in familiar patterns. Atoms combine in predictable ways. Chemistry follows well-worn paths. Now imagine those patterns playing out not just once, but across an enormous, perhaps endless canvas. Given enough space, arrangements repeat. Not because the universe intends them to, but because there are only so many ways to shuffle the same deck of physical possibilities. This leads to a quietly astonishing conclusion. Far beyond our cosmic horizon, there could exist regions that resemble our own in surprising detail. Galaxies arranged in similar spirals, stars with similar lifespans, planets orbiting in familiar rhythms, and if the universe is large enough, some of those regions could be almost identical to ours, down to the smallest details, with only slight differences scattered along the way. A cloud forming a little earlier, a star igniting a little later, a planet following a slightly altered path. This is one of the gentlest versions of the multiverse. It does not rely on quantum branching or cosmic bubbles colliding. It arises simply from scale, from the realization that if space is vast enough, possibility has room to repeat itself. Of course, this idea can feel unsettling. It brushes against our sense of uniqueness, our feeling that what happens here is singular and unrepeatable. But it's important to hold this thought carefully. Even if distant regions mirror aspects of our own, they remain causally disconnected. No signal travels between us. No influence crosses the expanding space. Whatever unfolds there unfolds without touching our lives in any practical sense. Meaning, then, does not dissolve. It localizes. It belongs to experiences, relationships, and moments within our horizon of time and light. The possibility of repetition elsewhere does not diminish the significance of what happens here, any more than the existence of many stars diminishes the warmth of the one that lights our days. This vastness can also bring a kind of quiet comfort. It suggests that the universe is not narrowly tuned to a single outcome, but generous with space and time. That complexity is not a fragile exception, but something that can emerge again and again under the same gentle rules. As we reflect on this, the multiverse begins to feel less like a dramatic claim and more like a calm consequence. If space is nearly flat, and if it extends far enough, then parallel regions are not exotic. They are simply far away. And with that realization, the idea of other worlds stops being a sudden leap. It becomes a gradual widening of perspective, one that starts with the geometry of space itself, and slowly carries us toward deeper questions about infinity, repetition, and the strange intimacy between scale and possibility. When the word infinity appears, it often arrives loudly, trailing confusion behind it. It feels abstract, untouchable, and somehow detached from everyday life. But in cosmology, infinity does not need to shout. It can speak softly, through consequences that follow calmly from simple ideas we already accept. If space extends far beyond what we can observe, and if the rules of physics remain the same throughout that vast expanse, then something subtle begins to unfold. The universe becomes a place where repetition is not forbidden. It becomes a place where, given enough room, familiar patterns quietly reappear. This is not the kind of repetition you see in a looping video or a copied file. It is more like walking along a shoreline scattered with pebbles. Each pebble is unique in detail, yet shaped by the same forces. Spend enough time along the shore and you begin to notice echoes, similar curves, similar textures, the same ideas, expressed again and again with small variations. In a universe that may stretch endlessly, the same principle applies. The building blocks of reality, particles, forces, and physical laws are limited in how they can combine within any given region of space. There are many possibilities, but not infinitely many in a finite volume. And when finite possibilities meet immense space, repetition becomes not just possible, but expected. This leads to one of the most quietly astonishing ideas in modern cosmology. Far beyond our cosmic horizon, there may exist regions that resemble our own in remarkable ways. Not exactly identical, but close enough to feel familiar. A galaxy shaped like ours, spiraling with the same elegance. A star similar to our Sun, warming a collection of planets. Perhaps even a planet with oceans, continents, and skies that look eerily like home. And if space truly goes on far enough, then somewhere, unimaginably distant, there could be a region almost indistinguishable from our own observable universe, not because it was designed to match it, but because the universe had enough room to explore every arrangement allowed by its rules. This idea can be unsettling when it's first encountered. It challenges our sense of singularity, the feeling that our story is uniquely placed at the center of existence. But cosmology gently invites us to release that assumption, not to diminish our experience, but to place it within a larger, quieter context. If distant regions mirror ours, they do so without interacting with us. The expanding space between regions ensures that no signal, no influence, no shared history can cross the gap. These are not parallel worlds that branch from our decisions. They are parallel regions, separated by distance so vast that it might as well be forever. To make this idea more approachable, imagine standing in a vast library that stretches beyond sight. Each book is written using the same alphabet and grammar. The stories differ, but the rules of writing remain constant. If the library is large enough, you would eventually find passages that echo one another. Similar scenes, similar characters, perhaps even entire chapters that feel familiar, until a small difference nudges the story in a new direction. The existence of such echoes does not make any single book less meaningful. Each story is still experienced locally, page by page, by its own reader. In the same way, our experience of the universe is anchored here, within our horizon of time and light. What happens beyond that horizon does not reach into our lives, shape our memories, or alter our relationships. This perspective offers a gentle reframing. Meaning does not come from exclusivity on a cosmic scale. It comes from connection, presence, and experience. The warmth of sunlight, the rhythm of breath, the shared moments that unfold within our brief window of awareness. These things matter precisely because they are lived, not because they're unique in an infinite census. There is also something quietly comforting in this vastness. It suggests that complexity and structure are not fragile accidents, balanced on a knife's edge. They may be natural outcomes that arise again and again wherever conditions allow. Life, in this view, is not a fluke that barely survived, but a pattern that can reappear given time and space. Of course, these distant doubles, if they exist, remain forever beyond our reach. No spacecraft can travel between them. No message can cross the expanding gulf. The universe ensures that these parallel regions remain separate stories, written in the same language, but never sharing pages. And yet, thinking about them changes how we see our own place. It softens the edges of isolation. It replaces the idea of a small, lonely universe with one that is vast, patient, and generous with possibility. As we let this idea settle, it becomes clear that this is only one pathway toward parallel worlds, a path born not from quantum strangeness or cosmic collisions, but from scale alone, from the simple recognition that if space is large enough, the universe has room to repeat itself, and as we continue drifting through these ideas, we'll soon turn to a very different source of multiplicity, one that emerges not from distance, but from the smallest events imaginable. Events so small that they quietly shape every moment of reality, whether we notice them or not. Up to this point, our journey has been guided by distance and scale. We've imagined space stretching far beyond our sight, repeating familiar patterns simply because there is enough room for them to appear again. But now the direction of our exploration gently turns inward, away from the largest structures in existence and toward the smallest events imaginable. It may seem surprising, but some of the strongest reasons scientists take parallel worlds seriously do not come from distant galaxies or ancient light. They come from experiments performed on particles so small that they defy our everyday sense of how reality should behave. At very small scales, nature does not move with the certainty we're used to. Instead of following a single, well-defined path, particles behave more like possibilities than objects. They spread, they blur, they explore multiple outcomes at once. And this behaviour is not due to our ignorance or faulty instruments. It is built into the way the universe works. To make this idea feel less abstract, imagine standing at a fork in a forest path. In everyday life, you choose one direction and leave the other behind. But at the quantum level, particles do not seem to make such clean decisions. Until they interact with something else, they behave as if they're taking all possible paths at the same time. This is not poetic language. It is the most accurate description scientists have found. Experiments repeatedly show that particles act like waves of possibility, spreading out and exploring every allowed route. Only when an interaction occurs, when something is measured, recorded, or affected, does a single outcome appear, and even then the deeper question remains. Did the other possibilities vanish? Or did something else happen? For a long time, physics avoided this question. The mathematics worked beautifully. Predictions matched experiments with extraordinary precision. The focus remained on calculating outcomes, not interpreting what they meant for reality itself. But over time, that silence became uncomfortable. If the equations describe many possible outcomes with equal legitimacy, why do we experience only one? What selects the particular result we see? Is there a hidden mechanism that collapses all other possibilities? Or is our experience only a small part of a much larger picture? These questions do not arise from philosophy alone. They arise from experiments that have been repeated, refined, and verified over decades. The strange behaviour of particles has been observed not just once, but countless times, under carefully controlled conditions. Consider a simple analogy. Imagine tossing a coin in a perfectly still room. In everyday physics, the coin lands heads or tails, and the other possibility disappears. But in the quantum world, the equivalent of that coin toss does not settle so neatly. The system carries both outcomes forward, at least mathematically, until something forces a resolution. What's unsettling is that the equations never say, and now only one outcome remains real. That instruction is not written anywhere in the formalism. It is something we add afterward, as an interpretation. This realization opened the door to a quiet but radical thought. Perhaps nature never chooses a single outcome. Perhaps every allowed outcome continues, each in its own unfolding story. In this view, reality does not collapse, it branches. This branching is not dramatic or explosive. It happens constantly, silently, at scales far below our awareness. A particle interacts, possibilities separate. Each branch evolves independently, carrying its own version of events forward in time. From within any one branch, the experience feels perfectly ordinary. There is no sensation of splitting, no awareness of alternatives. Life continues smoothly, as if only one outcome ever existed. This is why the idea is so difficult to grasp. From the inside, branching leaves no trace. From the outside, if such a perspective were possible, it would look like a vast tree of realities, continuously diverging at every moment. It's important to pause here and soften the image. This is not about dramatic choices creating new universes at every turn. It's about physical interactions, about particles colliding, decaying, scattering, about microscopic events that quietly influence everything from chemistry to biology. Every time light reflects off a surface, every time a molecule vibrates, every time a particle changes state, the underlying rules allow for multiple outcomes. And if those outcomes are all taken seriously, then the picture of reality becomes richer and more layered than our everyday intuition suggests. What makes this idea especially compelling is that it does not require changing the equations of physics. Nothing new needs to be added. No exotic forces are introduced. The mathematics remains exactly as it is. Only our interpretation of what the mathematics represents shifts. That shift is unsettling for some, comforting for others, and endlessly fascinating for many. It suggests that the universe is not a single thread, but a tapestry woven from countless threads, each following its own path. Still, this is not a claim of certainty, it is a proposal. One way of making sense of equations that already describe the world with remarkable success. Other interpretations exist, and scientists continue to debate which, if any, reflects reality most accurately. But what cannot be ignored is this. At the smallest scales we can probe, nature resists simplicity. It refuses to reduce itself to a single, predetermined story. Instead, it offers a landscape of possibilities, all equally real in the language of mathematics. As we sit with this idea, gently and without urgency, we begin to see how parallel worlds might emerge not from cosmic distance, but from the everyday fabric of reality itself. Not far away in space, but woven quietly into every moment that unfolds. And as this understanding settles, it naturally leads us toward the question that first brought this idea into focus. The question posed by a young physicist who looked at these equations and wondered whether the universe might be far more expansive than anyone had dared to imagine. It helps, sometimes, to imagine a quiet room, a desk scattered with papers, chalk dust lingering in the air long after the writing has stopped. Outside, the world moves on, unaware that something subtle and unsettling is taking shape inside that room. In the middle of the 20th century, physics was enjoying a period of remarkable success. Quantum theory worked. It predicted experimental results with astonishing accuracy. Engineers used it to build new technologies. Chemists relied on it to understand molecules. For most physicists, the job felt complete enough. The calculations worked, and that was what mattered. But for one young physicist named Hugh Everett, something about the story felt unfinished. Everett was not dissatisfied with the equations. He trusted them deeply. What troubled him was the way physicists talked about what the equations meant. Again and again, he noticed a quiet gap between the mathematics and the narrative wrapped around it. The equations described a world full of possibilities. Yet the story physicists told was a world where only one outcome ever truly happened. The moment of measurement, they said, caused reality to collapse, selecting a single result and discarding the rest. Everett paused at that word, collapse. He searched the equations carefully. He looked for the moment where nature was instructed to choose. He looked for the place where all other outcomes were erased, and he found nothing. No line that said, "And now the universe picks just one." To Everett, this felt less like an explanation and more like a convenient habit, a way of speaking that avoided discomfort rather than resolving it. So he asked a question that sounded simple, almost naive, yet carried enormous weight. What if the equations were telling the truth exactly as written? What if every possible outcome described by quantum theory actually occurred? In this view, there is no collapse, no magical moment where reality selects one path and abandons the others. Instead, when an interaction happens, reality branches. Each outcome continues forward, fully real, but no longer able to interact with the others. From within any one branch, the world feels continuous and stable. You see a definite result. Your instruments record a single value. Life goes on without interruption. The other branches are not experienced not because they vanished, but because they no longer overlap with your own. Everett did not present this idea as fantasy. To him, it was the most straightforward reading of the mathematics. It required no new rules, no special exceptions, sudden breaks in the laws of nature. The universe simply followed the equations everywhere all the time. But the response was not what he hoped. Many physicists found the idea disturbing, not because it contradicted experiments, but because it challenged intuition. The thought of countless parallel realities unfolding simultaneously felt extravagant, even wasteful. Why would nature be so excessive? Everett, however, saw the opposite. To him, forcing reality to collapse into a single outcome felt artificial. It added a mysterious process that no one could define clearly or locate precisely. Allowing all outcomes to exist felt simpler, cleaner, and more honest. Despite this, the scientific community was not ready. Everett's work was largely set aside. He completed his degree, stepped away from academic physics, and lived the rest of his life outside the spotlight of the ideas he'd introduced. Years passed. And then something interesting began to happen. Quantum experiments became more refined. Systems once thought too large to display quantum behavior began to show it anyway. Particles remained linked across distances. Interference patterns persisted in ways that resisted classical explanation. Again and again, the mathematics held firm, even as the intuitive stories around it strained. Gradually, physicists began to revisit Everett's question, not because it felt comfortable, but because it refused to go away. They noticed something important. The many worlds interpretation did not predict anything new or exotic. It predicted exactly what quantum theory already predicted. Its strength was not in adding features, but in removing assumptions. It stripped away the idea of collapse and allowed the universe to evolve smoothly without interruption. In this way, Everett's proposal shifted from being a radical speculation to being a serious contender among interpretations of quantum mechanics, not universally accepted, not proven beyond doubt, but no longer dismissible. What makes Everett's story especially fitting for a quiet exploration like ours is its tone. There is no dramatic revelation, no triumphant ending. There is only persistence. A question asked calmly, held patiently, and rediscovered when the time was right. It also reminds us of something deeper about science. Progress does not always come from new data alone. Sometimes it comes from looking again at what we already have and asking whether our explanations are truly necessary or simply familiar. As you sit with this story, you may notice a subtle shift in how parallel worlds feel. They're no longer distant regions beyond the horizon. They're no longer speculative bubbles colliding in the early universe. They're quiet companions to every physical process, branching gently whenever nature allows more than one outcome. And perhaps the most comforting part of all is this. Even if such branching occurs constantly, it does not disrupt your experience. You live within one continuous story, one unfolding thread of reality. The existence of other threads does not tangle yours. It simply means the fabric is richer than it appears from any single strand. With that thought resting gently in place, we can begin to explore why these branches, if they exist, remain invisible to us, and how the universe itself keeps their stories from ever overlapping again. By now, the idea of branching realities may feel less startling than it first did, not because it has become ordinary, but because it has been approached gently, step by step. And yet one question still lingers quietly in the background, waiting to be addressed. If reality truly branches so often, and if these branches are as real as the one we experience, then why don't we ever notice them? Why does the world feel so solid, so singular, so continuous? The answer to this question does not come from adding anything new to physics. It comes from understanding how complexity builds itself and how fragile connections quietly fade as systems grow larger. To ease into this idea, imagine two voices singing in perfect harmony. When their timing is exact, you hear a single, rich sound. But if one voice drifts slightly out of sync, the harmony softens. Drift a little more and the voices separate. Eventually, they no longer form a single song at all. They become independent melodies, each following its own rhythm. Something very similar happens in the quantum world. At very small scales, possibilities can overlap. Different outcomes can interfere with one another, reinforcing or cancelling out in delicate patterns. This is why quantum effects are often easiest to observe in tiny, carefully isolated systems. A single particle, a beam of light, a controlled experiment shielded from its surroundings. But the universe we live in is not isolated. It is warm, noisy, and full of interactions. Every particle is constantly bumping into others. Every system is surrounded by an environment, and every interaction leaves traces, however subtle, that spread outward at incredible speed. As these interactions accumulate, the delicate overlap between different possibilities begins to fade. Not abruptly, not violently, but steadily, like voices drifting apart in a vast echoing hall. Physicists use a technical word for this process, but it can be understood without it. What matters is the effect. The different possible outcomes of a system stop overlapping. They stop influencing one another. They become, for all practical purposes, separate. Once this happens, there is no way to bring them back together. This is why we do not see chairs in multiple places at once, or cats both awake and asleep in the same room. Not because such states are forbidden at the deepest level, but because the environment forces them apart almost instantly. The world around us acts like a constant observer, nudging reality into well-defined, stable forms. From inside one of these stabilized outcomes, the universe feels classical, predictable, solid. The branching that occurred beneath the surface leaves no ripples that we can sense. It is important to notice what this explanation does and does not do. It does not say that other outcomes vanish. It does not say they collapse into nothingness. It says that they stop overlapping with us. They drift out of phase like stories written in the same language but printed in different books, placed on shelves so far apart they will never touch. This quiet separation is why branching worlds, if they exist, remain hidden. Not because they are distant in space, but because they are distant in influence. They no longer share information. They no longer exchange signals. They become silent to one another. What makes this idea especially gentle is that it does not introduce sharp boundaries or sudden breaks. There is no dramatic moment where reality snaps. The separation is gradual, continuous, and inevitable in a universe filled with interactions. And this has a comforting implication. It means that the world you experience is not fragile. It is not constantly at risk of dissolving into confusion. The same processes that allow complexity to arise also protect it. They give us stable objects, persistent memories, and reliable cause and effect. Even if the deeper structure of reality is rich with possibilities, the surface remains calm. As experiments have grown more precise, scientists have observed this separation happening in larger and larger systems, not directly, but through the disappearance of interference patterns as systems interact with their environments. Each time, the same story unfolds. Isolation preserves overlap. Interaction dissolves it. This gradual loss of overlap does not require consciousness. It does not depend on human observation. It happens whenever a system becomes entangled with its surroundings, whether or not anyone is watching. This point is important and worth resting with for a moment. The branching of reality, if it occurs, is not driven by attention or awareness. It is driven by interaction, by the simple fact that nothing exists in perfect isolation for long. In this sense, the universe is constantly telling itself stories, and just as constantly separating those stories so they do not interfere with one another. Each branch carries on quietly, unaware of its siblings, unfolding its own consistent history. From your perspective, life feels continuous because it is. Your memories align, your environment behaves reliably, the past leads smoothly into the present. Nothing about this experience requires that other possibilities be erased. It only requires that they remain out of reach. And so, without drama or disruption, the many possible outcomes allowed by quantum rules become many quiet realities, each protected by the same processes that make the world intelligible. As we let this idea settle, we begin to see how branching can exist without chaos and multiplicity without confusion. Reality can be vast and layered, yet still feel intimate and stable from the inside. With this understanding in place, the path forward begins to shift again. From the quiet separation of quantum possibilities, we are gently carried back outward, to the early universe, where space itself may have undergone its own branching, long before stars, planets, or observers ever appeared. By now, the idea of branching realities may feel less startling than it first did, not because it has become ordinary, but because it has been approached gently, step by step. And yet, one question still lingers quietly in the background, waiting to be addressed. If reality truly branches so often, and if these branches are as real as the one we experience, then why don't we ever notice them? Why does the world feel so solid, so singular, so continuous? The answer to this question does not come from adding anything new to physics. It comes from understanding how complexity builds itself and how fragile connections quietly fade as systems grow larger. To ease into this idea, imagine two voices singing in perfect harmony. When their timing is exact, you hear a single, rich sound. But if one voice drifts slightly out of sync, the harmony softens. Drift a little more, and the voices separate. Eventually, they no longer form a single song at all. They become independent melodies, each following its own rhythm. Something very similar happens in the quantum world. At very small scales, possibilities can overlap. Different outcomes can interfere with one another, reinforcing or cancelling out in delicate patterns. This is why quantum effects are often easiest to observe in tiny, carefully isolated systems. A single particle, a beam of light, a controlled experiment shielded from its surroundings. But the universe we live in is not isolated. It is warm, noisy, and full of interactions. Every particle is constantly bumping into others. Every system is surrounded by an environment. and every interaction leaves traces, however subtle, that spread outward at incredible speed. As these interactions accumulate, the delicate overlap between different possibilities begins to fade. Not abruptly, not violently, but steadily, like voices drifting apart in a vast echoing hall. Physicists use a technical word for this process, but it can be understood without it. What matters is the effect. The different possible outcomes of a system stop overlapping. They stop influencing one another. They become, for all practical purposes, separate. Once this happens, there is no way to bring them back together. This is why we do not see chairs in multiple places at once, or cats both awake and asleep in the same room. Not because such states are forbidden at the deepest level, but because the environment forces them apart almost instantly. The world around us acts like a constant observer, nudging reality into well-defined, stable forms. From inside one of these stabilized outcomes, the universe feels classical, predictable, solid. The branching that occurred beneath the surface leaves no ripples that we can sense. It is important to notice what this explanation does and does not do. It does not say that other outcomes vanish. It does not say they collapse into nothingness. It says that they stop overlapping with us. They drift out of phase, like stories written in the same language but printed in different books, placed on shelves so far apart they will never touch. This quiet separation is why branching worlds, if they exist, remain hidden, not because they are distant in space, but because they are distant in influence. They no longer share information. They no longer exchange signals. They become silent to one another. What makes this idea especially gentle is that it does not introduce sharp boundaries or sudden breaks. There is no dramatic moment where reality snaps. The separation is gradual, continuous, and inevitable in a universe filled with interactions, and this has a comforting implication. It means that the world you experience is not fragile. It is not constantly at risk of dissolving into confusion. The same processes that allow complexity to arise also protect it. They give us stable objects, persistent memories, and reliable cause and effect. Even if the deeper structure of reality is rich with possibilities, the surface remains calm. As experiments have grown more precise, scientists have observed this separation happening in larger and larger systems, not directly, but through the disappearance of interference patterns as systems interact with their environments. Each time, the same story unfolds. Isolation preserves overlap. Interaction dissolves it. This gradual loss of overlap does not require consciousness. It does not depend on human observation. It happens whenever a system becomes entangled with its surroundings, whether or not anyone is watching. This point is important and worth resting with for a moment. The branching of reality, if it occurs, is not driven by attention or awareness. It is driven by interaction. By the simple fact that nothing exists in perfect isolation for long. In this sense, the universe is constantly telling itself stories, and just as constantly separating those stories so they do not interfere with one another. Each branch carries on quietly, unaware of its siblings, unfolding its own consistent history. From your perspective, life feels continuous because it is. Your memories align. Your environment behaves reliably. The past leads smoothly into the present. Nothing about this experience requires that other possibilities be erased. It only requires that they remain out of reach. And so, without drama or disruption, the many possible outcomes allowed by quantum rules become many quiet realities, each protected by the same processes that make the world intelligible. As we let this idea settle, we begin to see how branching can exist without chaos and multiplicity without confusion. Reality can be vast and layered, yet still feel intimate and stable from the inside. With this understanding in place, the path forward begins to shift again. From the quiet separation of quantum possibilities, we're gently carried back outward to the early universe, where space itself may have undergone its own branching, long before stars, planets, or observers ever appeared. Before there were stars, before there were atoms, before there was even light in the familiar sense, the universe passed through a moment so brief and so intense that it quietly shaped everything that followed. This moment did not last long by any ordinary measure of time, but its effects are still written across the sky today, faintly and patiently waiting to be noticed. To approach this idea gently, it helps to let go of the image of an explosion. The early universe was not a blast sending matter outward into empty space. There was no centre, no edge, no surrounding void. Instead, space itself was already there, and it began to change its scale. Imagine a tiny seed of space, smooth and tightly held, suddenly swelling, not by pushing against anything, but by stretching from within, like foam rising quietly as bubbles form and expand all at once. Every point moving away from every other point, not because they're travelling through space, but because space itself is growing between them. This is the calm heart of inflation. Inflation describes a brief period in the very early universe when space expanded at an extraordinary rate. Distances that were unimaginably small became vast in an instant. Regions that were once close enough to share heat and information were carried far apart, long before stars or galaxies had a chance to form. This sudden growth helps explain something that might otherwise feel puzzling. When we look across the universe in different directions, the oldest light we see looks remarkably similar. Temperatures differ only slightly. Patterns repeat with quiet consistency. It is as if distant regions once knew each other well, even though today they lie impossibly far apart. Inflation offers a simple reason. Those regions were once neighbours. They shared conditions, exchanged energy, and settled into a common state before being gently but decisively separated by the stretching of space. As inflation slowed and ended in our region, the universe transitioned into a calmer expansion. Matter cooled, particles formed, light began to travel freely. Over immense stretches of time, tiny differences grew into galaxies, stars, and eventually worlds like our own. All of this may sound like ancient history, but inflation is not just a story about the past, it is also a story about possibility. In some versions of inflation, the process does not end everywhere at once. Instead, it behaves unevenly. In certain regions, inflation slows and stops, allowing space to cool and structure to form. In other regions, it continues, quietly, persistently, stretching space further and further, long after our own cosmic neighbourhood has settled into its current rhythm. This idea can feel abstract, so let's return to imagery. Picture a field of growing foam. Some bubbles stabilise and hold their shape. Others continue expanding, forming new bubbles within them. Each stabilised bubble becomes its own enclosed region, while the surrounding foam keeps rising. In this picture, our universe is one such bubble. A pocket where inflation ended locally, allowing time, matter and structure to unfold. Beyond it, inflation may still be happening, creating other pockets, each separated from the rest by rapidly expanding space. From inside any one bubble, the universe looks whole, complete, self-contained. There is no sign of the foam beyond, no indication that other bubbles exist. The expansion between regions grows so quickly that no signal can cross the gap. No light, no message, no influence can travel from one bubble to another. This separation is not enforced by walls or barriers, it is enforced by growth. Space itself stretches faster than information can move. quietly ensuring that each bubble universe lives out its own history in isolation. What makes this idea especially striking is how little extra imagination it requires. Inflation was introduced to explain features of our own universe, its size, its smoothness, its structure. The possibility of many bubble universes arises not because scientists wanted more worlds, but because the equations allow inflation to keep going elsewhere. In other words, the multiverse does not appear here as a bold add-on. It appears as a side effect. This is a recurring theme in our journey. Again and again, the idea of parallel worlds emerges not from speculation layered on speculation, but from following existing theories to their natural conclusions, even when those conclusions feel larger than expected. It's also important to pause and acknowledge uncertainty. Inflation itself is strongly supported by observation, but its deeper details are still being explored. There are different models, different assumptions, different ways space might behave under extreme conditions. Some versions lead naturally to a cosmos that keeps making universes, others do not. Science has not yet settled which description is closest to reality, and that uncertainty is not a weakness, it is a quiet honesty. What we can say is this: inflation offers a coherent, elegant explanation for why our universe looks the way it does. And within that explanation lies the possibility that our universe is not alone, but one of many regions shaped by the same underlying process. If that is true, then parallel worlds are not hidden nearby, waiting to be discovered. They are far beyond reach, separated by expansion that began long before the first atoms formed. Their existence would be inferred, not visited, suggested by patterns, not revealed by travel. As we rest with this idea, it helps to remember that from within our own bubble nothing feels incomplete. The universe unfolds with remarkable consistency. Time flows. Causes lead to effects. Stars burn. Planets orbit. Life reflects on itself. Whether or not other bubbles exist, this one is real enough to hold meaning, wonder, and curiosity. And yet, the possibility remains that the vastness we see is only part of a larger process, that the early universe was not just the beginning of one story, but the opening chapter of many stories unfolding in parallel, each shaped by the same quiet expansion of space. With that thought drifting gently in place, we are ready to return once more to the oldest light we can see, and ask whether it carries, however faintly, a trace of contact with something beyond our cosmic bubble. If inflation were only a single, brief episode in the distant past, it would already be remarkable. A moment when space grew so quickly that it shaped the entire future of the cosmos. But some versions of the idea carry a quieter, stranger implication. Inflation may not have been a one-time event that ended everywhere at once. It may be something the universe learned how to do, and never fully stopped doing. To ease into this thought, imagine a landscape of gently rolling hills covered in mist. In some places, the mist thins and settles. In others, it continues to rise slowly but relentlessly, filling the valleys and climbing the slopes. From within any one clear patch, the world feels calm and complete. There is no obvious sign that the mist is still thickening elsewhere. This is one way to picture eternal inflation. In these models, inflation ends locally. In certain regions, the rapid stretching of space slows down, allowing matter and energy to take familiar forms. Particles appear, forces separate. Time begins to unfold in the way we recognize. These regions become what we would call universes. But outside them, inflation continues. Space keeps stretching, creating more room for new regions to settle out of the expansion. Over vast spans of time, this process can repeat again and again, producing many isolated pockets of calmer space within a much larger, ever-growing background. Each pocket is like an island forming in a cosmic ocean that never stops rising. From inside one of these islands, inside our own universe, everything feels stable. The laws of physics appear consistent. The past connects smoothly to the present. There is no sense of being born from a larger process, no hint of neighbouring islands just beyond the horizon. And that is not an accident. The expansion between these regions is not gentle, it is relentless. The space separating one bubble universe from another grows so rapidly that no signal can cross it. Light cannot travel fast enough. No message can be sent. No influence can be exchanged. Even the concept of distance becomes slippery, because the space in between is constantly being created faster than anything can traverse it. This is why eternal inflation does not suggest a multiverse you could visit, explore, or map. It suggests a multiverse defined by permanent separation. Not separated by walls or dimensions we might one day access, but by the very mechanism that gave rise to the universes themselves. Each bubble universe lives out its own history, unaware of its siblings. Within this picture, differences between universes are not only possible, they are natural. When inflation ends in one region, the details of how it ends can vary. The balance of forces may settle slightly differently. The properties of particles may take on different values. The overall behaviour of the universe may follow a different long-term path. These differences are not chosen. They emerge from chance and variation during the settling process, much like snowflakes forming unique patterns as water freezes under changing conditions. Some universes may expand too quickly for structure to form, others may collapse too soon. Some may never produce stars, a few may develop long-lived galaxies, chemistry, and complexity. And within an enormous collection of such universes, it becomes less surprising that at least one looks like ours. What's important to notice here is the shift in perspective. Instead of asking why our universe has the exact properties it does, we begin to ask a different question. Given many universes with many possible properties, what would it take for observers to arise at all? This does not replace physics, it reframes part of the puzzle. Eternal inflation does not claim that our universe was designed for life, or selected with intention. It suggests that life appears where conditions allow it, and only in those regions can questions about the universe be asked in the first place. From this point of view, our universe is not special because it exists. It is special because it is observed. And yet it's worth slowing down here and keeping our footing steady. Eternal inflation remains a hypothesis. It is strongly motivated by certain models and supported indirectly by how well inflation explains what we see. But it has not been confirmed in its eternal form. There are alternative models where inflation ends everywhere, once and for all. Science has not yet chosen between these possibilities. What keeps eternal inflation in the conversation is not certainty, but coherence. It fits naturally with existing ideas. It doesn't violate known laws. And it offers a framework that makes sense of features that otherwise feel oddly precise. It also carries a kind of quiet elegance, a universe that gives rise to many universes, not through drama or intention, but through simple repetition. Expansion leading to separation, separation leading to diversity, diversity leading, in rare pockets, to complexity and reflection. There is something almost meditative about this image, a cosmos that keeps creating, patiently and without preference, each universe unfolding its own story, never intersecting, never interfering, yet all born from the same underlying process. From within our own bubble, this larger picture remains invisible, but that invisibility is not evidence against it. It is a consequence of how inflation works. The same expansion that may create many universes also ensures that each one feels alone. And so, we find ourselves once again at the edge of observation, looking at a universe that feels complete, while entertaining the possibility that it's part of something much larger. As we drift forward, the question becomes more focused. If other bubble universes exist, is there any chance, however faint, that their presence could have left a trace? Not a message or a map, but a subtle mark in the oldest light we can see. With that question in mind, we return gently to the sky, and to a quiet irregularity that has been waiting patiently for interpretation. We have been here before, quietly circling this idea from different directions. At the very beginning of our journey, we noticed something unusual in the oldest light we can see, a region of the sky that seems slightly colder than expected, a place where the smooth glow of the early universe dips, just enough to catch a careful eye. Now, after exploring inflation, eternal expansion, and the idea of bubble universes, we return to that place with new context, not to force an answer, but to ask a gentler, better informed question. What if the cold spot is not just an oddity, but a trace? The light we are talking about here is ancient beyond imagination. It was released when the universe was still young, long before stars ignited or galaxies formed. It has been travelling ever since, stretching and cooling as space expanded until it finally reached us. This light carries a record of conditions from a time when everything was closer together, when the universe still bore the imprint of its earliest moments. Most of this light is remarkably uniform. Its temperature varies only slightly from place to place, like the surface of a calm lake disturbed by faint ripples. Those tiny variations are expected. They reflect the small irregularities that later grew into the cosmic structures we see today. But the cold spot stands out. It is larger than typical fluctuations, colder than expected, and shaped in a way that has invited careful scrutiny, not because it breaks the rules outright, but because it sits near the edge of what those rules predict. There are several ways to explain such a feature, and honesty requires that we hold all of them gently in mind. One possibility is statistical chance. In any large dataset, rare patterns can appear without deeper meaning. Roll enough dice, and unusual sequences eventually show up. The universe is vast and the sky is large. It may simply be that one region happened to cool a little more than average, without implying anything extraordinary. Another explanation points to large-scale structure. Between us and that patch of ancient light, there may lie an enormous region with relatively little matter, a vast underdense area that subtly affects the light as it passes through. Over billions of years, this journey could slightly alter the temperature we observe today, producing a cold region without invoking anything beyond known physics. These explanations are plausible, they are actively studied, and they may turn out to be correct. But there is a third possibility, quieter and more speculative, that becomes meaningful only after we have considered inflation and bubble universes. If our universe formed as one bubble among many, then in its earliest moments, before space expanded enough to separate everything completely, it may have brushed against another bubble. Not a violent collision like crashing objects, but a gentle overlap in the fabric of space itself, a brief interaction leaving behind a subtle imprint. In this picture, the cold spot would not be a photograph of another universe. It would not be a message, a portal, or a window. It would be more like a bruise, a scar left behind by an early contact, long after the contact itself has become unreachable. This distinction matters. Science does not expect other universes to announce themselves clearly. If they exist, They are separated by expansion so vast that direct observation is impossible. The only traces we could hope to see would be indirect, statistical, and deeply embedded in the structure of our own universe, a slightly unusual pattern, a deviation that doesn't quite fit the simplest expectations, something that invites explanation without demanding one. Researchers have explored what such a signature might look like, not in detail that needs equations or diagrams, but in general character. A region where the temperature shifts more smoothly than random fluctuations would suggest. A pattern that aligns with how early space might respond to an interaction between expanding regions. So far, the results remain inconclusive. Some analyses suggest the cold spot could be consistent with a bubble interaction. Others argue that known explanations are sufficient. New data has refined the picture, but not resolved it completely. The anomaly remains, quietly resisting a final verdict. And that, in a way, is the most honest place for it to rest. The cold spot does not prove the multiverse. It does not even require it. But it does something subtler. It keeps the question open. It reminds us that our understanding of the early universe is still incomplete, and that some features may point beyond the simplest stories we tell. This is how science often advances at the deepest levels. Not through decisive moments, but through persistent curiosities. Features that do not go away. Questions that remain interesting long after they are first asked. What's especially fitting for a calm exploration like this is how modest the cold spot truly is. It does not shout. It does not dominate the sky. It sits quietly among countless other measurements, noticed only because we have learned to listen carefully. Whether it turns out to be chance, structure, or something more exotic, it has already served a purpose. It has encouraged us to think more deeply about the early universe, to consider possibilities that stretch beyond a single isolated cosmic history. And perhaps that is enough for now. The multiverse, if it exists, is not something we stumble upon easily. It does not reveal itself through spectacle. It whispers through patterns, through consistency across theories, through hints that align without quite converging. As we let this thought settle, the focus begins to shift again, away from cosmic collisions and ancient light and toward a different kind of question. Not about how many universes there might be, but about why this one looks the way it does, why its laws sit within narrow ranges, why its conditions allow complexity, chemistry, and consciousness to arise at all. That question has been waiting patiently in the background, and now, with all these pieces gently in place, we are finally ready to approach it. As our exploration continues, the idea of parallel worlds gently changes its shape once again. So far, we've imagined other universes separated by vast distances, or by rapid expansion that keeps regions forever apart. Now the picture shifts, not outward into deeper space, but sideways, into dimensions we do not normally perceive. This does not mean travelling through portals or slipping between worlds. It means reconsidering what space itself might be capable of holding. To make this idea approachable, imagine a large, flexible sheet stretched tightly across a frame. Place a small weight in the centre, and the sheet bends slightly. Roll another weight nearby, and it follows a curved path, not because it is pulled directly, but because the surface beneath it has changed shape. This image has often been used to explain gravity, but now imagine that this sheet is not alone. Picture many such sheets stacked closely together, like pages in an enormous book. Each page feels complete to the characters living on it. They move forward and backward, left and right, entirely unaware that other pages exist just a tiny distance away, in a direction they cannot access. In some theories, Our universe is like one of these sheets, a three-dimensional surface, sometimes called a brain, embedded within a space that has more dimensions than we can observe directly. Matter and light remain confined to this sheet, while gravity, which is far gentler and more elusive, may be able to stretch between sheets. From within our own sheet, everything appears ordinary. Space has three familiar directions. Time flows forward. The laws of physics behave consistently. There is no immediate sign that additional dimensions exist, because their influence is either extremely subtle or effectively hidden at scales we can measure. If other sheets exist nearby, they would be parallel in a very literal sense, not far away in distance, but offset in a direction that does not belong to our everyday experience. These neighbouring universes would not overlap with ours. They would exist alongside it, separated by dimensions that are folded, compact, or otherwise inaccessible. This idea can feel strange at first, but it arises from attempts to unify the fundamental forces of nature into a single, consistent framework. In these efforts, extra dimensions are not introduced for drama. They appear because the mathematics becomes simpler and more harmonious when space has more room to work with. In such models, collisions between sheets are sometimes considered as possibilities, not collisions in the everyday sense of objects crashing, but brief encounters where two surfaces come close enough to interact. In some speculative versions, such interactions could release enormous energy, producing events that resemble the beginning of a universe. These ideas are sometimes described with dramatic language, cosmic fireworks, titanic encounters, but it's important to keep the tone grounded. This is one framework among many, a way of imagining how multiple universes might coexist without sharing space in the way we understand it. There is no experimental confirmation that such neighbouring sheets exist. No observation demands them, and yet the idea remains intriguing because it fits within broader attempts to understand gravity, space, and the unification of forces. What makes this idea gentle enough to include in our journey is not its certainty, but its restraint. It does not claim to explain everything. It does not insist that our universe must have neighbours pressed up against it. It simply suggests that reality may be layered in ways that are not immediately visible. For our purposes tonight, this framework serves as a reminder. Parallel worlds do not all have to arise in the same way. Some may be separated by distance, others by expansion, still others by dimensions that remain folded beyond perception. Each approach carries its own assumptions, its own questions, and its own limits. None stand alone as definitive answers. Together, they form a landscape of possibilities, different ways the universe might be larger than it appears from within. As we step back from this idea, there is a sense of returning to firmer ground, not because these ideas are dismissed, but because they are placed where they belong, as speculative extensions, not as the core evidence for the multiverse. They enrich the picture without overwhelming it. And as we gently let these layered universes fade into the background, another question moves quietly into the foreground. A question less about where other universes might be, and more about why this one looks so precisely arranged. Why its laws seem balanced just well enough to allow structure, stars, and observers to exist at all. That question has lingered beneath every version of the multiverse we've explored, and in the next part of our journey, we'll finally allow ourselves to face it directly. By this point in our journey, the idea of multiple universes has taken on many gentle forms. Some worlds are far away beyond the horizon of light. Others branch quietly from microscopic events. Still others may form as bubbles or lie beside us like neighbouring sheets. Now, the idea shifts again, away from space and time as we usually imagine them, and towards something more abstract. This is where reality begins to resemble structure rather than scenery. To approach this calmly, imagine a series of rooms, each contained within a larger room. Inside the smallest room, life unfolds normally. People walk, think, and observe. From their perspective, the walls define the whole of existence, and yet, beyond those walls there is more space, more structure, more rooms nested within rooms. This image captures the heart of the simulation idea. The simulation hypothesis suggests that a universe like ours could exist as part of a larger computational structure, not necessarily as a game or illusion, but as a detailed process unfolding according to rules. If such simulations are possible, then in principle there could be many of them, and within each, the inhabitants would experience their world as entirely real, because for them, it is. What matters most here is not whether we are simulated, but what the idea does to the multiverse picture. If one simulated universe can exist, then many could exist. Simulations could contain simulations of their own, creating layers within layers, each one internally consistent, each one hosting observers who experience meaning, continuity, and reality from the inside. This does not replace other multiverse ideas, it multiplies them. A universe born from inflation could contain simulations. A quantum branching universe could branch within a simulation. These frameworks are not mutually exclusive. They stack gently on top of one another, forming a hierarchy of possible realities. It's important to keep the tone grounded here. The simulation idea is not supported by direct evidence. It does not arise from cosmological observation or particle experiments. It arises from reasoning about information, computation, and what complex systems might be capable of given enough resources. For a calm exploration like ours, it helps to treat this idea not as a claim, but as a thought experiment, a way of stretching our intuitions about what it means for something to be real. And as soon as we do that, another idea begins to feel less strange. The mathematical multiverse takes one more step away from physical imagery. Instead of focusing on space, time, or computation, it asks a simpler but deeper question. Why does this universe follow these particular rules? Mathematics describes the universe with astonishing precision. Patterns written on paper seem to match the behavior of matter and energy with eerie accuracy. Over time, some thinkers have wondered whether this is because the universe is built from mathematics, rather than merely described by it. In this view, every consistent mathematical structure exists in its own right. Each structure is a universe. Some are simple, some are complex. Most do not allow stable patterns, memory, or observers. A small subset does. Our universe, in this picture, is not special because it was selected. It is special because it is inhabitable. Again, this idea should be held gently. It is not an experimental proposal. It does not predict specific observations. It sits at the boundary between physics and philosophy, where language becomes softer and certainty fades. What makes it relevant to our story is not its truth, but its role. It shows how the multiverse idea can arise not only from physical theories, but from reflections on structure itself, from asking why the laws of nature are expressible at all, and why they seem finely arranged to support complexity. Handled carefully, this idea does not feel cold or mechanical. Instead, it can feel strangely inclusive, a universe of structures where reality is not a single privileged pattern, but one of many ways consistency can unfold. For our purposes tonight, this framework serves as a quiet boundary marker. Beyond this point, the multiverse becomes increasingly abstract, increasingly philosophical, useful for reflection, but no longer anchored to observation in the same way. And that's perfectly fine. Not every idea needs to be proven to be meaningful. Some exist to widen perspective, to soften certainty, to invite humility. They remind us that our current understanding, however powerful, may be only one way of organizing experience. As we let these abstract universes drift gently into the background, the focus naturally returns to something more immediate. Not how many universes there might be, but why this one seems so carefully balanced. Why its laws sit within narrow ranges. Why small changes would have led to a very different outcome. That question does not belong only to philosophy. It arises directly from physics, and in the next part of our journey, we will approach it not as a mystery to be solved, but as a pattern to be understood, slowly, patiently, and without urgency. As our journey moves forward, the focus shifts once again, not outward to distant universes, and not inward to abstract structures, but towards something quietly puzzling about the universe we already know well. A puzzle that has been sitting in plain sight, patiently waiting to be noticed. When physicists study the laws of nature, they often describe them as a collection of balances. Not balances in the sense of perfect symmetry, but balances in the sense of delicate relationships. Values that sit within narrow ranges. Relationships that, if adjusted even slightly, would lead to a universe that behaves very differently from the one we experience. To make this idea feel intuitive, imagine a large control panel filled with dials. Each dial controls something fundamental: how strongly matter clumps together, how quickly stars burn their fuel, how stable atoms are, how easily chemistry can unfold. Turn one dial a little too far to the left, and stars may never ignite. Turn another slightly to the right, and stars may burn out so quickly that complex structures never have time to form. This image is not meant to suggest that someone actually turned these dials. It is simply a way of describing sensitivity. The universe appears to be responsive to small changes in its underlying settings. For example, if the processes that govern how matter attracts matter were slightly different, the universe might never have formed galaxies. Matter would remain too diffuse, drifting endlessly without gathering into stars, or it might clump too strongly, collapsing rapidly into dense objects before stable systems could emerge. In another direction, if the balance that governs how stars release energy were altered just a little, stars like our sun might not exist at all. They might burn so fiercely that they exhaust their fuel in a cosmic instant, or glow so faintly that planets never receive enough warmth for complex chemistry. These examples are not pulled from imagination alone. They arise from detailed studies of how physical laws interact to produce structure. What makes them striking is not that life requires special conditions, we expect that, but how narrow those conditions appear to be. Small changes can have large consequences, and this is where the sense of fine-tuning enters the conversation. The universe looks not just orderly but delicately arranged. Its laws do not merely allow complexity, they seem to sit right at the edge of what makes complexity possible. This observation has led to many responses over the years. Some see it as evidence of design. Others see it as a sign that deeper, as yet unknown principles must exist, forcing the universe to take these values necessarily. Still others see it as a clue pointing toward a broader cosmic context. This is where multiverse thinking begins to feel less speculative and more explanatory. If there were only one universe, with only one set of possible laws, then the question, why these values, would feel pressing, almost unanswerable. Why should the universe land so precisely within the narrow range that allows stars, chemistry, and observers? But if there are many universes, each with slightly different settings, then the question softens. Most universes would be empty, short-lived, or structureless. A few would allow complexity, and only in those rare universes could observers arise to notice the question at all. This does not solve the puzzle completely, but it changes its character. Instead of asking why the universe was set up for life, we ask why we find ourselves in a universe where life is possible. The answer becomes less mysterious, not because the universe was chosen, but because observers can only appear where conditions allow them to exist. This perspective does not remove wonder, it redirects it. The universe does not need to be arranged with intention to produce meaning. It only needs to be generous with possibility. Given enough variation, complexity becomes not inevitable, but expected somewhere. It's important to pause here and keep the tone grounded. Fine-tuning does not prove the multiverse. It does not demand it. It simply makes the multiverse an appealing framework, one that allows sensitivity without surprise. And crucially, this reasoning does not depend on exact numbers or technical constants. We do not need to list values or quote precise measurements. What matters is the pattern, the feeling that the universe operates within narrow margins, where small changes would lead to dramatic differences. This is why fine-tuning resonates so strongly. It speaks to intuition, to the sense that the universe is not sloppy, not random in an obvious way, but carefully balanced, whether by necessity, chance, or selection across many worlds. As we sit with this idea, the conversation naturally turns toward a principle that helps articulate it more clearly. A way of framing observation itself as part of the story, not as a force that shapes reality, but as a filter that shapes what can be noticed. That principle has a quiet name, and it has been guiding parts of cosmology for decades, often misunderstood, sometimes misused, but always returning to the same gentle insight. And that is where our journey will drift next. After spending time with the idea of fine-tuning, it becomes natural to ask a quieter question. Not why the universe has the properties it does, but why we are here to notice them at all. This is where the anthropic principle gently enters the story. Despite its intimidating name, the idea itself is simple, almost modest. It does not claim to explain how the universe came into being. It does not propose new forces or hidden mechanisms. Instead, it reminds us to pay attention to the conditions required for observers to exist in the first place. To ease into this, imagine walking through a vast forest filled with countless clearings. Some are dark and tangled, others are flooded or frozen. A few, scattered sparsely, are calm enough to linger in. If you find yourself standing in one of those calm clearings, it would be a mistake to conclude that the entire forest was designed for comfort. It would be more accurate to say that only in such clearings could you stop and look around. The anthropic principle applies this logic to the universe. In its most cautious form, often called the weak anthropic principle, it simply states that our observations are conditioned by the fact that we exist. We can only observe a universe whose laws allow observers. This is not a profound revelation, but it is an important reminder. It prevents us from asking certain questions in misleading ways. For example, asking, why does the universe allow life? Can quietly assume that life was the goal. The anthropic perspective reframes this as, given that life exists, what kind of universe would we expect to observe? The shift is subtle, but it changes the tone of the question entirely. In a universe, or a multiverse, where many different conditions are possible, it becomes less surprising that we find ourselves in one of the rare regions where complexity can arise. Not because such regions are common, but because only in those regions could observers ever appear. There is also a stronger version of the anthropic idea, sometimes called the strong anthropic principle. This version suggests that the universe must have properties that allow observers to exist. It is often interpreted in very different ways. Some hear intention in it, others hear necessity, still others treat it as philosophical reflection rather than a physical claim. For a calm exploration like ours, it is best to hold this stronger version lightly. not as a statement of purpose, but as a way of noticing that the universe's laws and the existence of observers are deeply entangled questions. What matters more than labels is the underlying insight. Observation is not a neutral act. It comes with conditions. Just as a fish can only observe water-rich environments, observers can only arise in universes that support stable structures, long-lived energy sources, and complex interactions. This idea sometimes becomes tangled with discussions of consciousness and measurement in quantum theory, so it's worth clarifying gently. In quantum physics, observation does not require awareness or intention. It refers to interaction, systems influencing one another, information becoming distributed into the environment. When anthropic reasoning is used carefully, it does not claim that observers create the universe. It claims that the universe we observe is filtered by the requirement that observers exist within it. The filter comes first, the observation follows. In the context of the multiverse, this filter becomes especially meaningful. If there are many universes with many different properties, then most will be empty or chaotic. A small fraction will allow complexity. An even smaller fraction will allow beings capable of reflection. From within one of those rare universes, it might feel as though everything was improbably arranged. But from a broader perspective, the improbability softens. Given enough variation, rare outcomes are not surprising. They are inevitable somewhere. This does not remove mystery, it reframes it. Instead of asking why this universe is perfect for life, we ask why life appears where it can. The answer is not dramatic, it is quietly logical. There is another idea that often accompanies anthropic reasoning, sometimes called the landscape. This word is used to describe a vast range of possible universes, each with its own combination of laws and properties. Like valleys in a mountainous terrain, some regions are stable and fertile, others are steep, barren, or short-lived. Observers, in this picture, arise only in the gentle valleys. Again, this is not a claim of certainty. It is a way of organizing thought, a framework that helps us understand why the universe might appear finely balanced, without requiring that balance to be unique or intentional. What's especially important for our journey tonight is the emotional tone of this idea. The anthropic principle does not strip the universe of meaning. It does not say that our existence is accidental or trivial. It says something quieter and perhaps more grounding. It says that our presence is conditional, that life arises where it can, and that the fact we are here, reflecting on the universe, is already evidence that certain conditions were met. Meaning then does not come from being cosmically central. It comes from being locally real, from being part of a story that could unfold only under specific circumstances, and did. As we let this idea settle, it prepares us for one final turn. A possibility that blends physics, evolution, and cosmic history into a single, poetic image. An idea that imagines universes not just appearing, but reproducing. Each new universe slightly different from the last. It is speculative. It is far from proven. But it offers a gentle way to think about why the universe might favour certain patterns over others. And with that curiosity resting softly in place, we are ready to approach the final reflection of our journey. As our journey nears its quiet conclusion, the universe offers one more idea, less as a claim and more as a possibility to sit with. An idea that weaves together themes we've already encountered: variation, selection, and the slow shaping of complexity over time. This idea suggests that universes might not simply appear at random, but could give rise to new universes through processes already familiar to us. Not through intention or design, but through repetition and consequence, through something like cosmic inheritance. To approach this gently, imagine evolution not as a race, but as a patient wandering. Over time, traits that support persistence become more common, not because they were chosen deliberately, but because they last. They leave descendants. The landscape slowly fills with patterns that happen to endure. Now imagine this process unfolding not within life, but within the cosmos itself. The proposal, often described as cosmological natural selection, suggests that black holes might play a role in the birth of new universes. When a massive star collapses into a black hole, the interior conditions become extreme beyond our current ability to observe directly. Instead of ending reality, these conditions might allow space itself to branch, forming a new expanding region, a universe of its own. In this picture, each black hole becomes a kind of seed. Not a doorway we can travel through, but a point where a new cosmic story might begin, disconnected from its parent yet shaped by its properties. What makes this idea especially interesting is how it connects to fine tuning without invoking intention. If universes can give rise to new universes, and if each new universe inherits slightly different properties, then over many generations, certain traits could become more common. Universes that produce more black holes would have more offspring. Over time, the population of universes could become biased toward those with laws that favour star formation, long-lived structures, and gravitational collapse, conditions that also happen to support complexity and eventually observers. This does not claim that life is the goal. It claims that the same conditions that allow stars to form and collapse might also allow chemistry and reflection to arise as byproducts. It is a quiet idea, elegant in its restraint, and deeply speculative. There is no direct evidence that black holes give birth to new universes. No observation can peer inside them. No signal escapes their boundaries to confirm or deny what lies beyond. This idea remains firmly in the realm of theoretical exploration. And yet, it fits a familiar pattern. It takes processes we already know exist, collapse, variation, selection, and asks what they might imply when extended to cosmic scales. It does not demand new forces or miraculous interventions. It simply wonders whether the universe might be self-reproducing in a way that echoes patterns seen elsewhere in nature. Whether or not this idea turns out to be true, it serves a deeper purpose in our exploration. It shows that the multiverse, in its many forms, is not about diminishing meaning. It is about relocating it. If there are many universes, then ours is not special because it exists. It is special because it is experienced. Because within it, awareness arose, curiosity unfolded, questions were asked. Out of countless possible realities, this is the one you are in. That fact alone carries weight. The multiverse does not erase the intimacy of your experience. It does not turn your life into a statistical accident. Instead, it frames existence as something that emerges where conditions allow and becomes meaningful through presence and connection. In a vast cosmos, rarity does not imply insignificance. A rare flower in a desert is not less beautiful because deserts exist. Its beauty lies in the fact that it blooms at all. As we bring our journey to a close, it's worth returning to the quiet humility that has guided us throughout. We do not have proof of parallel worlds. We may never have direct proof. The universe may remain forever larger than what we can test. But the hints persist. Patterns in ancient light, equations that allow more than one outcome, the delicate balance of physical laws, the coherence of ideas that arise independently from different corners of science. Together they do not force a conclusion, they invite reflection. Science at its best does not rush toward answers, it listens. It follows implications patiently. It accepts uncertainty as part of understanding, not as a failure of it. And in that spirit, the idea of parallel worlds remains alive, not as a destination we are trying to reach, but as a question we are learning how to hold. So as we settle into the quiet at the end of this exploration, you might let one final thought drift through your mind. Out of all the possible ways reality could have unfolded, you're here, in this universe, at this moment. A small region of awareness within a vast and mysterious whole. That does not make the universe smaller. It makes this moment precious.